So, hi everyone, I'm Melinda, and I'm here to talk about our favorite thing, cloud-native distributed systems. Let's see if I can get the screen share to work. Screen, is it sharing? Check. Yep. Sweet. So yeah, as Daniel mentioned, I'm going to start with some slides. Then I will show a live demo of a request-response architecture and how we can move it to an event-driven one. And then we'll close with Q&A or just chatting about what is on all of your minds. After the talk, I am going to post these slides, a link to the code for the demo, and other notes to this URL here at eggybits.com. And as Daniel mentioned, I work for Eggy, where we love cloud-native distributed systems. Spent time at Visco and some other places before that. Hi, Shruti. So, if you're writing software that touches the internet today, there's no getting around it. You're building a distributed system. And what that means is that some of your software is running in a mobile device, maybe. Some parts of your software are running in a web browser. Some parts are running on the server, probably many parts are running on many servers. And all of these parts are calling each other over a network, which may or may not be working at any point. It might be running out of batteries. I might have dropped the computer, might have an exploded hard drive. But even in this environment, your software is expected to stay up and running perfectly, even though any of its parts might be gone, which is difficult. Cloud-native software is inherently distributed, and distributed systems are just difficult to design, to build, to understand, and to operate. But that's why our jobs are fun. When we build our systems, we're usually designing for three main concerns. One, reliability, like how we can make sure that the system continues to work correctly, performantly, even if there's a hardware fault, a software fault, or human error sometimes. Scalability, how to make sure we have reasonable ways of dealing with our systems growing, whether that's in data, compute, or team size. And maintainability, like how do we make sure that all of the different people that are definitely going to be working on our app, on our system over time, can understand and work on it productively. But one overarching concern about all of this is how we can keep complexity under control. Like when we start building something, it can be simple, it can be delightful, it can be clean, but as our projects get bigger, they often become complex and difficult to understand, like this. And this complexity slows down everybody who needs to work on the system. We get tangled dependencies, hacks, special cases to work around problems, an explosion in the state space. You know, you've seen all of these things, I'm sure. And one way that we as an industry have tried to manage this complexity is by breaking our software down into independently deployable services, which we call microservices, right? This has many advantages. Services can be worked on in parallel by different teams or different people. Each service can focus on a specific domain. And together, that gives us a lot more flexibility than a monolith, in theory, in how we can solve larger problems. But that's only true if we decompose our software in a careful way and use patterns that fit the specific business context that we are working in. For example, if we aren't careful, we could end up with software that is still tightly coupled, but now has an unreliable network between every piece of business logic, and is hard to deploy, and is basically impossible here to debug. Okay, so why is this, and how can we avoid that? As mentioned, one key property of our software architecture is how our microservices interact with each other. Our software, if it's decomposed, only works if multiple services work together. And the default way that we do interaction nowadays is with request response, using synchronous network calls. So in this model, we basically try to make requests to a remote network service look like calling a function in our programming language within the same process, which seems really convenient at first, but seeing remote calls as function calls is fundamentally a flawed premise, because a network request is just not a function call. It's really different. A local function call is predictable and either succeeds or fails, depending on parameters that are totally within your control, right? But a network request is unpredictable. It could return successfully, albeit much more slowly than a function call. It could return successfully, but way more slowly. The network could be congested, or the remote service could be overloaded, so it might take 5 minutes or 20 seconds to do the exact same thing as the thing that returned in 150 milliseconds. The request or response could get lost due to a network problem. And if you don't get a response from a remote service, you basically have no way of knowing whether the request got through or not. Maybe the requests are actually getting through and only the responses are getting lost. So it's probably not safe for you to retry it unless you've built in a mechanism for deduplication. The cloud is just a rough environment to be in. It's really, really different from a single computer. And because of this, our distributed software, when it interacts using request response, can be incredibly difficult to reason about. Imagine that you have on the order of hundreds or thousands of services communicating to each other in a point-to-point way, how many different point-to-point connections that might be. And that's what large distributed service architectures that use request response often look like. Like this, for example, is Netflix's architecture around 2015 from a reInvent talk at the time. It's about, I think, 850 microservices at the time. It shows a network of their services and the synchronous runtime dependencies on every services, on other services. And this representation is sometimes known as a Death Star diagram. You can see that as the number of services grows over time, the number of synchronous interactions grows with them, somewhere between linearly and quadratically. And if you zoom into any one service, this, for example, is the call graph for a single Netflix service from that same talk. I thought this was funny, the list of movies service, or LOLOMO. These are all the services that the LOLOMO service has to talk to in order to return a response. And you can see that this one service depends on so many other ones, and any of these n dependencies being down can cause availability issues for our one service. And apart from just availability, we get latency, which grows with the depth of this dependency graph. We probably need to coordinate read times between which of these is querying the data store to make sure you're not reading an old piece of data. We're probably going to find it extremely difficult to reason about the state of the system at any point in time. There's just a lot going on, and this is just one call. And so one solution to this availability problem, discussed in depth in this paper here from Google, Calculus, is just to make sure that your individual services have significantly higher SLAs than what you need your system as a whole to have. So if you need 99.99% availability, maybe you need 5 or 6 nines in your downstream services, which, good if you can get it. Not all of us are Google. But you can also do things, and we've built these tools as an industry, like make automatic request retries when you don't get a response back with back pressure. You can add caching between clients and servers. You can have multiple redundant copies of services that can take requests when one copy is broken with live and readiness checks to make sure we're getting the live ones. We need dynamic service discovery, load balancing, circuit breaking in order to make all of this possible. Different kind of traffic control mechanisms. We have service meshes now, like Linkerd and Istio, to make all of this more transparent to the user. Distributed tracing, of course. I mean, these are all standard cloud-native patterns, but these are standard patterns because trusting request response to work in a hostile environment like the cloud is inherently risky. And so much of the mindshare in the microservices landscape, the libraries, the tooling, the documentation, blog posts, books, diagrams, talks, assumes this model of services calling each other synchronously. And I think it's a little unfortunate that we so often conflate the core values and goals of microservices with a specific model for their implementation. Request response isn't what microservices are, really. This is also a hostile environment. But What if instead of having to patch these solutions for resilience on top of request response, which as we noted has fundamental flaws, we could change the problem to a simpler one and try to just not bind our services together as much with synchronous ties. And as an analogy, I think the request response model really matches our sequential imperative programming model of making in-place state changes on a single computer. We've seen that that imperative model isn't perfectly suited for our distributed environment, but another programming style might match more closely. Functional programming in this analogy. Functional programming describes behavior in terms of the immutable input and output values of pure functions, not in terms of mutating objects in place. And we've seen in the last few years how thinking about things in this more functional way helps in other parts of the stack. On the web, for example, we've had reactive frameworks like React and Redux and Vue, Elm before that almost everyone has shifted to after seeing how they can simplify things. On mobile, the new generation of UI frameworks on both iOS and Android is functional and reactive. And we've had libraries for reactivity in business logic like RX for a while, Combine on iOS more recently. And on the infrastructure side, we've seen how declarative APIs like Kubernetes and infrastructure as code tools like Terraform have made things so much easier to reason about, and GitOps promises to take that further. But we're still early in adopting this in backend application development. What would it look like if we did extend the functional programming analogy to microservices architecture? Well, it's basically event-driven architecture. Like functional programming, it lets us know consistently the state of a system as long as we know its input events. So there are a lot of different definitions of what could be called an event-driven system, but really the common thing is that the thing that triggers code execution in an event-driven system doesn't wait for any response, it just sends it and then forgets about it. So in this diagram on the left, there's a request and a response. When a request is received, the receiving server has to return some type of response to the client. Both the client and the server have to be alive, well, and focused on each other in order for this to work. But on the other hand, on the right, there's an event-driven service. The service that consumes an event does something with it, yes, but it does not have to send any response to the thing that originally created the event that triggered it. Only this service has to be alive for this code to be run. It doesn't depend on other services being there. It's not coupled to the thing that produced the event. It doesn't have to know about that producer at all. And the way that this usually looks in practice is that we use a message broker or distributed log to store these events. These days, this is usually Kafka or Kinesis. And the events are split into different streams called topics, which get partitioned across a horizontally scalable cluster. And each of our services can either consume from one or more topics, produce to one or more topics, do both, do neither. And we'll see this in a working example in a bit. But why is this better? It's a really different way of having programs interact. And if we're going to make this change, we better have some really good reasons. And I think the biggest reason is the decoupling and easy composability that this gives us around our business logic. By getting rid of these point-to-point synchronous flows, our system can become much simpler. Instead of having to work to add things and having that work scale quadratically, or almost so, because each new thing has to be hooked up to every existing thing, it becomes a much simpler task to just plug new services in or change services that are there. We can break these long chains of blocking commands where one piece being down at any given time means that all of these are unavailable. And if we zoom out then to a whole organization, these design principles let us build composable systems, really, at a large scale. So in a large org, different teams can run independently. They can design and build services that consume from topics or produce to topics. Since any topic can have any number of independent consumers, no coordination is required to set up a new consumer. And they can be deployed at will, built with different technologies, different languages, different data stores, etc. Each team can focus on making their particular part of the system do its job well. And as a real-life example, this is how this worked at Visco. Visco is a photo and video sharing consumer platform, high surety, mostly used by Gen Z. Users have their own profile. They can follow each other users and get their content in their feed. It's a social network, but no ads. What happens if a user follows another user? Well, the first thing that happens here is they hit a synchronous follow service, which then tries to get that information into this distributed log, Kafka, as soon as possible. And once it's there, it can be used for many things, right? It can get consumed by a feed fan-out worker, so the follower can get the followee's posts injected into their feed. It gets consumed by the push notification pipeline, so the followee can see they've gotten a new follower, and so on and so on. And the key is that you can really keep on plugging more consumers without affecting the original follow service, right? You can add monitoring, so you can see if the rate of follows goes way down and business metrics might be messed up because we shipped some weird version of the app. Or if it goes way up, if something strange is happening. We can add an abuse prevention mechanism in case something strange is happening. You can add analytics in case you need to make a report to Wall Street, and so on. All of these systems can be developed independently and connected and composed in a way that is and feels robust. Another side benefit is that you get asynchronous flows for free. We don't have to, like we used to, do a bunch of orchestration to set up batch jobs with like Airflow or something. If we handle the real-time case with events, we can do offline jobs by default. And this functional composition makes things easier to trace as well. We get a central immutable saved journal of every interaction and its inputs and outputs. So we can go back and see exactly where something failed. In order to get this with request response, we'd have to invest a ton in a full distributed tracing system. And even then, we might not see where latencies are being hidden. Another reason why event-driven systems are helpful is that they can provide scale by default and make some of the patterns we talked about for resilience in request response service architectures unnecessary. So these were some of the things we talked about earlier. The distributed log really acts as a buffer. If recipients are unavailable or overloaded, it will automatically redeliver messages to processes crashed. So this makes these retries less necessary. The log avoids the sender needing to know the IP address and port number of the recipient, which is particularly useful in the cloud when computers come up and down. So we don't need as much complex service discovery and load balancing. And we talked about distributed tracing earlier. A third thing is that there's something called, I guess, polyglot persistence nowadays, where we all use lots of different kinds of databases. There's no single one-size-fits-all database anymore that's able to fit all the different access patterns efficiently. For example, you might need users to perform a keyword search on a dataset, and so you need a full-text search index service like Elasticsearch. You might need a specialized database like a scientific or graph database to do specialized data structure traversals or filters or something like that. You might have a data warehouse for business analytics where you need a column-oriented storage engine or something like that to do queries performantly. When new data gets written, like how do you make sure that it ends up in all the right places, right? If something goes wrong, how do you recover? What if you write to one of these things and not the other? And so one thing, I guess the way that we used to do this is that we would write to all of the databases from one microservice, from one service, one synchronous service. So dual writes or triple or quadruple writes, whatever. But we've seen how that's fragile and also how it's theoretically impossible to make dual writes consistent without distributed transactions. Like you can't really guarantee that a write that goes to MySQL and also Mongo will write to both places or neither. So instead, one solution is to use event-driven systems to do what is called change data capture. This is an old idea where we let an application subscribe to a stream of everything that's written to a database, and then we can use that stream to do these things: update search indexes, invalidate caches, create snapshots, and so on. There are open source libraries for this now. There's Kafka, there's Debezium, which uses Kafka Connect. And increasingly, databases are starting to provide this sort of a stream as a first-class interface. Mongo does that, for example, now. But at Visco, because we started doing this back in 2016, before this was really a thing in the industry, we had our own version. And so if we go back to the follows use case, the way that that event gets into the distributed log in the first place is that the follows service writes to an online transactional database, say something like MySQL or MongoDB, and then our change data capture service writes every change to the distributed log, where any number of consumers can do whatever they want with it. This ends up actually being a nice way to migrate off the monolith. That helped us. You can let the monolith keep doing the initial database write and suck those events into your event store with database change capture, and then pull out all of the reads from your monolith, plus all of the extra stuff that the monolith does for every write into composable workers, and then eventually kill the write from the monolith. And as a side benefit to this helps us fix one of the most common things that catches us in microservice architecture, where we do have a bunch of independently deployable services, but they all share a single database. We usually would rather have our data not be this coupled, but it's hard to unbundle it, and change data capture makes it much easier. One more thing, we also can save much richer data with event-driven systems if we want to. Writing data as a log can really produce better quality data by default than if we update a database directly. And that really has more to do with the way that we think about what an event is. So for example, if someone adds an item to their shopping cart, I'm buying furniture, and then removes it again, those add and delete actions have informational value. If we delete that information from the database when a customer removes an item from the cart, we've just thrown away information that might have been valuable for analytics and recommendation systems, right? And this approach, where we are storing each action that's happening in our system as an immutable fact, is usually given the name event sourcing, which comes originally from the domain-driven design community. Kind of like change data capture, event sourcing involves saving all changes to the application state as a log of change events. But instead of having something where part of the application is allowed to use the database in a mutable way and update and delete records as it pleases, in event sourcing, our application logic is explicitly built on the basis of immutable events. So the event store is append only. Usually you can't update or delete anything. And you derive the current state of the world from the stream of events. So you can imagine say, a version control system like Git, where instead of storing the actual files, imagine we stored only the diffs from the beginning of time, and then to get to a copy of your current working tree, you would basically aggregate over all the diffs over time. That's kind of like how event sourcing systems are. In a fully event sourced system, the current state is derived, which is valid. Both of these approaches are valid. This and the mutable version, they come with slightly different trade-offs in practice. But regardless of which one we use, the important thing is to save facts as they are observed into an event log. And as a bonus, this falls out of all of the other reasons, but because I love machine learning, this turns out to be really good for machine learning. There's this idea of software 2.0, which is that increasingly we're going to want to plug machine learnable programs into different parts of our software systems, where we can get better results by learning something than by hand coding a program. Like, let's say we want to tune a database index with a model here, or decide whether this request is from a legitimate actor over there. And inserting ML like this will really just not be tractable if we do this in a point-to-point request response way. Our software will become totally incomprehensible. But if we've already switched to using an event-driven system, where the pluggable data integration is already there for us, adding ML becomes much less painful. That said, there are some things to watch out for with this. The biggest one is concurrency management. If we have distributed data management, how do you make sure that you read your writes, or you read all the implications of your writes? We don't really have time to go into this because it's a deep theoretical issue, but that Martin Kleppmann paper goes into it in a lot of depth. I'll link it later. Request response doesn't really solve this issue either, but I mean, we should. You do have to be thoughtful about your schemas, how you choose to structure your event data. Since your events are now your programming interface for all other actors, you have to handle backward and forward compatibility with them just like you would with an API. Empirically, I found this less work than versioning request response APIs, but it's something to think about. There are mature systems like Protobuf and Avro for this that are quite good. Just, don't try hand rolling something on top of JSON for this. Privacy. With GDPR, with a lot of privacy concerns, because event systems make it easier to distribute our data and have things be more modular, we now have to think about how we can delete things that need to be deleted. Event-driven systems do have nice mechanisms for this, but it is something that we need to think about. But the biggest gotcha is, although it's becoming less and less true, event-driven interactions are not the norm, right? So there are just fewer libraries and tools and blog posts and example repos about this than request-response architectures right now. But running Kubernetes or using infrastructure as code wasn't the default a few years ago either. So I mean, we've seen how the industry moving to these things has made our lives easier. So I posit that we'll see more and more of these things as we go forward. OK, I will stop talking now and try to show you some code, if that's OK, if we still have time. Yeah, sounds good. All right, cool. Let's see if this can work, maybe. So we are going to run a breakfast delivery service. Yep, breakfast. No worker exploitation here. First on request response microservices, and then on event-driven microservices, so we can see the difference in behavior. So first, our system will look like this. We have a web client. We have an order service, which gets called by this web client. And on getting the request, the order service will call the payment and the delivery service synchronously. Shout out to my boss at Eggy for writing this, Vivian Liang. Thanks, V. And then we'll change it to look like this. We'll still have an order service, which still gets called by our web client, but instead of calling the payment and the delivery service synchronously, it will write an event to Kafka. And we'll have a payment and a delivery worker that each read from Kafka and does its own work. So we're going to call them workers to emphasize that they don't take synchronous calls. And so we're going to run this whole distributed system on this computer, a 2014 MacBook, which hopefully will let us run all of this. So this is our demo code repo, which you can see on GitHub later. Each of our services is a folder in Go services. And each of these main.go files compiles into a binary with Bazel, like so. And here in Protos, the Protos directory, you can see the service definitions for each service. So for instance, the order service has an RPC called create order. The payment service has an RPC called process payment. And the delivery service has an RPC called deliver order. And in the logic for the order service, if we go back to that, we call process payment and deliver order synchronously. And we return successfully to the client only if both of those are successful. So let's run them. This is our order service, which synchronously calls our payment service and our delivery service. And let's go to our breakfast web app. This is also in the repo, so the whole thing should be runnable with instructions from the README. So let's say we want an egg, and a pancake, some bones, and maybe some baguettes. OK, let's place our order. OK, it's on the way. You can see that the order service called the payment service, got a successful response, called the delivery service, got a successful response, and then returned a response to the client synchronously. OK, great. So let's say that now we want more breakfast. But let's say that we're having some iffy network day or something like that, and our delivery service is intermittently available to the order service. So let's emulate that by terminating it. And then let's try again. So this time I want, I don't know, only potatoes. But let's try. Now I can't get them. So what happened, the order service got the request from the client, reached the payment service that succeeded, tried to reach the delivery service, couldn't, and then failed because the order service couldn't reach the delivery service for a second. Okay, so that's what happens when there's some iffy cloud stuff going on. Now we're going to do an architecture refactor and switch to an event-driven mode of doing things. So instead of calling the other services directly, like we were doing before, we have a new version of the order service, an async version, which instead will write to Kafka. And we'll have a payment and a delivery worker that each read from Kafka and do their own work. So you can see in this version of the order service, this still uses the same service interface to the client, but in this handler, we are producing to Kafka instead of calling these services synchronously. And in the workers, so this is the delivery worker, for example, we are just consuming from Kafka in this handle function. So let's see what that looks like. Let's go to the async version, and run these guys. We'll run the order async API, the payment worker, and the delivery worker. You know, if it wants to build. Maybe we can cut some of this stuff. Hello. Sorry. So let's go back to our breakfast app and make another order. This time we just want an egg, and maybe some pancakes, and maybe some bones. Okay. And now this is successful. The user-facing behavior is the same as it was before, which is expected when everything's going well. And you can see the order async API wrote the events to Kafka, the payment worker read it and processed the payment, the delivery worker read it and started the delivery. But okay, let's say just like before, we're having another iffy cloud day, and our delivery worker is going up and down. Let's try to emulate that by terminating it. And then let's try again. This time, I don't know, more potatoes. All right. And now my request succeeds because our backend trusts that this delivery worker is going to come back. Right. And so when it does, it should catch back up and process the order that it missed. So there we go. So the user-facing behavior in this case is quite different from the synchronous one when the cloud environment is being a cloud environment and there are some intermittent issues. But one more thing, so let's see what this looks like if we want to add another piece of business logic or functionality. Let's say, for example, that we want to send users a push notification if they order breakfast to let them, think hungrily about the items that are coming. Well, we think that this should be a straightforward operation. We can just add another worker that's consuming from the same topic. So the idea is that it's trivially easy to add non-trivial functionality to the system. We can just write another worker, and we don't have to change the original order service at all. So let's try that. Make you bigger. And now we should just be able to run this guy. And let's order one more time. Let's say some chocolate, some baguettes. Well, it's not a really nutritious breakfast. Let's try actually something different. Let's do an egg, a pancake, a potato. I feel like I'm being judged for my breakfast choices at the moment, but that's fine. All right, let us submit our order. Please give me breakfast. And the idea is that you can do the same thing to, say, add a worker that sends your breakfast info to a big breakfast advertiser, or suck order info into an analytics database for data science or any other type of work. So you can see we got our push notification processed here, and let's look at my phone here. Let's see if I have anything embarrassing on my phone before I do this. Okay, let's see. Please send breakfast. Okay. Oh, you can't see my screen. Oh, maybe you can see my screen. Maybe I need to stop sharing my screen. But you can see that breakfast is on the way. Yeah. Okay. So I will stop talking now.